Hey everyone, this video is going to cover some of the challenges we face with the implementation of hydrogen as a future fuel source. This is hydrogen. Hydrogen is the first element on the periodic table. It is made of one proton and one electron, making it the lightest element, and is considered very reactive. Being the most abundant element in the universe, it composes about 75% of the total mass. When in an environment composed of only itself, hydrogen will bond with one another to create an H2 molecule, where at standard pressure and temperature it is in a gaseous state. While hydrogen gas is highly combustible, it only takes up about 0.00005% of our atmosphere. Perfect, as we don't want Earth to become a mini star of sorts. By no means is it a rare thing, however, as hydrogen atoms are often bonded with other types of atoms in the form of water, natural gases, and coal, among other things. Hydrogen is being used across many industries on a mass production scale, being a crucial part of our everyday lives. It is an important step in the petroleum refining process, as well as the synthesis of ammonia. In ammonia production, the way that this is achieved is through the Haber-Bosch process, a chemical process combining hydrogen and nitrogen at extreme temperatures, roughly 500 degrees Celsius, and pressures around 148 to 296 atmospheres, with the use of an efficient iron-based catalyst to allow the reaction. About 80% of this ammonia is used in the fertilizer industry. While hydrogen as a potential fuel has been known since about the 19th century, in recent years it has resurged in popularity as a potential fuel source of the future. But why use hydrogen as fuel? There's been a move to minimize global carbon emissions, and hydrogen has shown a lot of potential as a carbon-free fuel, more specifically in the transportation industry. Face value, it looks really nice. You take a couple molecules of hydrogen, a molecule of oxygen, make them go boom and bam, you get good old H2O energy. So much nicer than the carbon dioxide and whatever your car's catalytic converter couldn't catch coming out of the tailpipe. Now if you look deeper into it, other issues arise. Excess hydrogen in the atmosphere causes harm because both hydrogen and methane interact with hydroxide. This disrupts the rate of dissipation of methane, a very strong greenhouse gas. This isn't to mention the overwhelming majority of hydrogen production is through fossil fuels, defeating the whole notion of clean energy. For this reason, we will be focusing on green hydrogen, a method which involves using zero-emission sources of electricity, such as wind and solar power, to power electrolysis, a process which separates water molecules into hydrogen and oxygen. The process of producing hydrogen by electrolysis and burning hydrogen are essentially opposite of each other. When burning hydrogen, it takes a minuscule amount of energy to start combustion at 0.019 millijoules. Since it's such a small number, we'll take this out of consideration, so we can assume that both producing hydrogen and burning it is dealing with the same amount of energy, just reversed. With this in mind, the energy released by the combustion reaction is 285.8 kilojoules per mole. This is called the higher heating value. We can divide this by the molecular weight of the hydrogen molecule, 2.01568 grams per mole, to find that this is the equivalent of 141.7 megajoules of energy per kilogram of hydrogen. The lower heating value takes into account the heat energy lost during the reaction. Being at 48.6 kilojoules per mole, we have a remaining 237.2 kilojoules per mole being the maximum amount of electrical energy we can extract from the reaction, assuming there are no heat recovery systems in place. This is the equivalent to about 117.7 megajoules per kilogram, as we use the same calculation as the higher heating value. Unfortunately, there is no such thing as 100% efficiency. In any source of energy, there are going to be losses from start to finish, with hydrogen being no exception. If we consider the reverse of this process, converting water into hydrogen and oxygen, we will be using the theoretical 117.7 megajoules per kilogram of electrical input to produce the hydrogen. While there have been advancements seeing upwards of 95% efficiency in the production of hydrogen using electrolysis, current technology, commercially in use, is expected to have a lower 75% efficiency. To find the energy we need to put into the electrolysis process, we will divide the lower heat value by the commercial efficiency, giving us an input needed at 156.9 megajoules per kilogram of H2. While hydrogen has a phenomenal energy density by mass, for comparison, gasoline averages about 45 megajoules per kilogram, it's got one issue. It really likes being a gas, and gases are great at taking up as much space as they can. If hydrogen is at 1 atmosphere of pressure, in 0 degrees Celsius, its density sits at about 9 times 10 to the negative fifth kilograms per liter. If we multiply this by our lower heating value of 117.7 megajoules per kilogram, we get just about 10 kilojoules per liter of energy density by volume, which really sucks when gasoline sits at a much higher 34.6 megajoules per liter. So how do we fix this issue? By increasing the volumetric energy density through compressing and cooling. There are two main ways of storing hydrogen: in a compressed gaseous state, or as LH2, aka liquid hydrogen. In gas form, it is commonly compressed between 350 bar and 700 bar. The theoretical work required to compress hydrogen to 350 bar is about 3.78 megajoules per kilogram of H2, and at 700 bar, it becomes 4.86 megajoules per kilogram of H2. In liquid form, more energy is required, as it calls for an extreme temperature of only 20 Kelvin. The theoretical energy needed for liquefaction sits at 8.28 megajoules per kilogram of H2, with an additional 2.34 megajoules per kilogram of H2 needed to convert the hydrogen into a lower energy equilibrium state. As the focus for hydrogen is in the transportation industry, let's look at cars today. Most manufacturers opt for Type 4 hydrogen tanks, storing hydrogen up to 700 bar. As this is after electrolysis, we estimate that there is 117.7 megajoules per kilogram worth of usable hydrogen that we need to compress. Theoretically, we have to use 4.86 megajoules per kilogram of H2 of work to compress to 700 bar. The energy used here is the equivalent of 4.1% of the hydrogen being used for compression. In practice, efficiency complicates things. The efficiency of a compressor that has to compress H2 to 700 bar is estimated at 49%, as well as an additional 0.72 megajoules per kilogram of H2 needed for cooling to negative 40 degrees Celsius. We can list our knowns here. To find the work that the compressor does, we divide the theoretical work needed to compress the 700 bar by the efficiency of the compressor, giving us 9.9 megajoules per kilogram of H2 of work needed. Further, we can add the 0.7 megajoules per kilogram needed for cooling to find 10.6 megajoules per kilogram is needed to compress and cool the hydrogen to the state. To find the efficiency of this process, we divide the 10.6 megajoules per kilogram H2 by the lower heating value, 117.7 megajoules per kilogram, to see that an equivalent of 9% of the H2 present to be used in compression. Finally, to find the total amount of energy used so far, we take the energy used in electrolysis and add the energy we need to compress and cool to find that we have used 167.5 megajoules per kilogram of H2. Again, as the pressure for hydrogen fuel is seen more so in the transportation industry, it's important to see what type of effective energy usage we may be seeing from the hydrogen tank within the car to its mechanical output. Assumptions we are going to make are as follows. 1. The fuel cell used is a polymer electrolyte membrane, or PEM for short, as it's the industry standard. This fuel cell has a typical efficiency of about 60%. And 2. Per Department of Energy estimates, the efficiency of converting electrical energy to mechanical work in electric cars lies at about 59 to 62%. So, we will be taking the median of this and assuming 60.5% efficiency. We can find the overall efficiency of this process by multiplying the two efficiencies given, finding it to be about 36.3% efficient. Now we can find the total energy required from electrolysis to power output, dividing the total energy thus far by 36.3% efficiency, yielding 461.4 megajoules per kilogram H2 of energy required. Finally, we can approximate the total efficiency of this process by taking the lower heating value and dividing it by the amount of energy required to discover that the amount of energy needed to produce hydrogen is 4 times that of the energy that will be returned. One more consideration. Like any other gas, leakage can pose a massive problem throughout the process. Not only does it indirectly increase methane levels in the atmosphere, but it also could have the potential to be a massive loss of fuel. The exact numbers for quantity of hydrogen lost through the process isn't well known, but some studies suggest that it could be from 2 to 4% in a more ideal situation to as high as 10 to 15% in the more extreme situations. Apart from methane and lost energy, a nice quality that hydrogen has is that it has an extremely fast diffusion rate, meaning that the chances of a leak causing similar results as an unfortunate blimp incident are greatly reduced. Thank you for making it to the end of the video. Here are the academic sources we used through the last 10 minutes or so, as well as which AI image generators we used.